Our next speaker is Kireeti. Kireeti is the CTO of Juniper Development and Innovation. He is known for his leadership in IETF for MPLS, TE, ISIS, OSPF, GMPLS, VPN, etc. That's good one, right? Before this new role, Kireeti was also worked in Contrail as a CTO. That's another startup, successful SDN startup. And before that, Kireeti was a longtime CTO at Junos. Kireeti is known as a deep thinker. I had the pleasure working with Kireeti for many years. Welcome, Kireeti.
Thank you. So before I start, I should say that I do come to this conference and I love coming here, but I'm usually not a speaker at the keynote. The reason I am this year is twofold. One is Yakov retired, and I know that there are some speakers in the audience that are very happy that he did. But I think that's a big loss to our industry. He was a really good thinker. He came up with lots of very good ideas. BGP, the whole internet runs on that. And of course, he has a way of getting to the point, whether it's in his own presentations or in the questions that he asks of others, and we will miss that. I also want to thank Remy and Michelle for, they probably had no one else to pick, so they picked me. But,
by the way, Kireeti, Yakov still have some YouTube you can watch online.
Sure, yeah.
Speech.
If you have Yakov withdrawal, you can watch Yakov on YouTube. So I'm going to talk about this. Looking at Loa's presentation, I got really scared because I'm going to talk about data plane control plane separation versus impedance matching. And so there are a whole bunch of us sort of charging down this path of data plane, control plane separation. And I want to get in front of the buffalo herd and say, whoa, go that way. And so seeing Loa's presentation, I think I'm going to try something different. So I've told you before about my view of SDN and the fact that we shouldn't really be focusing on the data plane, control plane separation. SDN has been saying for a long time, this is it. We need to be separating control plane, data plane. Here are all the great reasons for doing that. And what I basically said is, yes, if you do that, what you'll end up with is you've taken the control plane, separated it, and then you built up this APIs so network applications can be built. And then you think about network transforms to achieve whatever state transitions that you want. So your network apps are essentially doing that. And this seems like a reasonable way of doing things, but it does get you to a very imperative approach to what you want to do in the networks. So you think in terms of writing C or Java or whatever your favorite imperative language is to do these network transformations. That's all fine and good as an academic, but if you look at what's really going on in a router or a switch, the academic view is that you have a control plane and a data plane. And there's this notion that they don't really work well together between different vendors. Well, the entire internet runs on this. So it's more or less pretty interoperable. You do have the occasional bug, you do have the occasional glitch, but it mostly works. The actuality of a router is you have a control plane, a data plane, and a configuration layer. And the configuration layer that's on the router determines what are the services that that router is going to perform. And so this is the part that's very, very non-standardized. The way you might, if you consider, for example, an MPLS, BGP MPLS VPN, you can configure it on a Cisco iOS, you can configure on Cisco XR, you can configure it on Juniper, you can configure on ALU. The service that you get will be almost the same. This all works well together in the control plane, in the data plane, policies work, all great, but how you configure them is so very different among all these platforms. So this is where we need some degree of standardization. This is where we need more agility. People want to bring up services more quickly. People want to try out new things. People want to do mashups. And this is where we're failing. And control plane data plane separation doesn't get you there. This is a message I gave many, many years ago, 2 years ago. And I'm glad it's sticking because listening to Sunil's talk, the ideas of abstraction, the ideas of declarative, say what you want, not how to do it, are coming through. So great. The question for the industry is, once you're past this thing and you say, I want to give you the service agility via abstraction, I want to give you the service agility via declarative statements, I want to take this control, the config layer off the box, create this orchestration layer, and give you these RESTful APIs with which you can interact. Great. I think if we did all this, we would be in a much better position. So we're done, right? The topic is closed. We can move on and do some real work now? It seems not. What we're seeing is that the control plane, data plane separation argument still flies, and people still want to do this. And you might ask, and to channel Yakov, you might ask the question, what is the practical problem you're trying to solve? What is the benefit of doing this? And so people will say, oh, if I separate the control plane and the data plane, I can work on the southbound API, and the southbound API is going to transform everything and make me really happy. Well, okay. The southbound API is definitely an interesting topic, and our current choices for the southbound are very poor, so fixing it would be helpful. But there's a much more pressing problem. There's a practical problem that we have to solve. And this is the part where I get in front of the thundering herd and say, ooh, don't go this way, go this way. So you have this herd of buffaloes going down this path of, we need to solve the southbound, we need to define this. Maybe you change it in a big way, but the current course that people are taking is essentially, this is where all the action should be. Well, what is the pressing problem? Let's take some use cases at the network edge. If I think about these different functions or use cases, and I think about a 10 terabit box, and a 10 terabit box is not very big these days. And I take, say, mobile subscribers and say they get 10 megabits each, I'll do some oversubscription. How many subscribers do I have to take care of if I have this 10 terabit box? So you do the math, and you might come up with your own math. The numbers are not really particularly important, but the idea is important. The amount of CPU work that you have to do, the control plane work, that you have to do to keep up with, in this case, 4 million subscribers, the amount of state you have to keep, the amount of, in Sunil's words, dealing with all the mobility and what's going on with the different customers is very, very high. If you take wireline subscribers, you typically give them more bandwidth, and you typically, maybe subscribe them somewhat less. You still have a lot of work to do in the control plane, dealing with them, and in the scale in terms of the sheer number of them. And maybe you don't have as much mobility there in principle, but you do have people coming on and going off, and you have to deal with that. Business customers, generally a much smaller scale than wireline or wireless subscribers, but they come in with requirements like, I want to do a VPN, or I want to do business internet. And so the number of routes and the number of other things they carry is quite high. So the control plane work on the CPU side, on the cycles, on the compute side, may be medium, but the control plane work on state could be much higher. Peering, it depends on if you're peering at 10 gig or 100 gig. It's not as bad, but again, it depends on who your peers are and what kind of glitches are happening at your peers. The main thing here is that you have a number of services at the edge, which at 10 gig makes a lot of difference. It does put a lot of strain on the control plane. If you look in the network core, life is somewhat different. Actually, in the core, you have potentially higher bandwidths, but less work to do. So I won't point out all the details here, but one of the things that people were very concerned about is the number of transit RSVP LSPs. It used to be the case with transit RSVP LSPs, you'd be very worried about what would happen if a link flapped or there was a massive rerouting of LSPs. Used to be a big problem, used to create a lot of strain on the control plane. With some of the more recent work, this has reduced dramatically. So in the end, if you say, what is the control plane work needed in the core of the network, it's much, much less. The one case where you might have a lot of work is if you have a pure IP network and you have IBGP running throughout on every box, then BGP flaps go directly into the core and you have to be able to deal with it. It's not horrible, but you can bypass that by having a tunneling system. So MPLS or whatever your favorite tunneling is, and keep the churn on the edge and keep the center of your network relatively free. If you do that, your core doesn't really have a huge control plane issue. Clearly, these use cases are snapshots in time, and so the numbers that go with it, the kind of oversubscription, we're probably going to get to a place where people are going to try to oversubscribe less, because as people use applications like video, oversubscription doesn't work really well. But the main fact is, pick your own numbers, pick your own point in time, make your own predictions. You will find that there's a big control plane requirement, and the control plane requirement is growing. So what's the problem? I mean, this is a statement of current situation. The problem is that there's a control plane data plane divide. Intel, back in about 2004, realized that they can't just keep ramping up the gigahertz, so they got up to about 3.8 or so gigahertz, and they realized that ramping up the gigahertz beyond that meant that the chip gets too warm and they can't cool it, and the yields were really dropping. So they said, we need a different approach. So they went to multi-core. And what multi-core meant is I'm going to give you lots of different cores, and they can then work independently on the problem that you want them to work on. I build general purpose computers, so I have to continue to work on all the problems that you work on. I mean, these computers have to work on all the problems that you care about. So they can't sort of by default say, I'm only going to work on this subset of problems that are easy to parallelize or easy to deal with in different ways. So they did a good job with multi-cores over time. Initially, they actually put two separate independent CPUs on one die, but eventually they said, I'm going to have lots of cores, I'm going to have cache coherency, I'm going to do all this stuff. But because they do these general purpose things, they cannot cater to the problems that are easy to decompose. They also wanted, from a programmer point of view, to make their lives easier, to retain the image, the illusion of a single memory. So they had to do all the cache coherency stuff. Also, they know that they have a big problem with memory bandwidth, but they want to use commodity memory, so they can't use specialized memory for this. If you contrast, so the growth is relatively flat, and you'll see that in a second. So if you contrast this with what's happening in forwarding is a problem that's easy to decompose. You can say, I'm going to have multiple engines, and this engine will work on this set of ports, or this set of flows, or this, these routing tables, or something. And you can decompose the problem. And so, yes, you're getting 100 gig in, but maybe there's a way that I can work on the packets that are coming in parallel. And so the problem for forwarding has been relatively easier. It's not a general purpose compute thing. It's how do I get these packets in and out of my system quickly. We have come to the point where we use specialized memory for this. So we're not sort of bound to using commodity memory chips. We're using specialized memory for this because we also have the problem of high memory bandwidth into the chip. So in general, forwarding has forged ahead pretty fast. So while CPU growth has been relatively flat, forwarding has been pretty fast. So you can see that here. And I'll say a few things about the numbers. Please don't get hung up on the numbers, whether it's numbers for the use cases that I gave you or numbers for these CPUs. I took a sampling of CPUs that I thought were high-end CPUs. You might have a different sense of those. I took them across time from 2008 till today and trying to look forward. And essentially, these are very, very high-end CPUs. And there's this website you can go to, CPU Benchmark, that does testing of these. And what they do is come up with numbers for each of these things. So if you look at the i7-965, it has a pass mark number of 5,800. And if you look over time, newer and newer chips from Intel, you can see how they've grown. So you went from 5870 in 2008 to about 12,700 in 2011 and so on. And you can see the factor by which they've grown. So essentially, the control plane has grown by a factor of 2.17 in 3 years from 2008 to 2011. And in another 3 years, it grew by a factor of 2.9, again, counting back to 2008. And in 2015, they're somewhere around 4 times as fast as they were before. They've increased the cores, they've increased, the clock speed is pretty much not increased. They've increased the memory bandwidth a little bit, they've done a few other tricks they could, but there's not a whole lot they can do. What they have done very effectively is reduce the power, but the raw throughput that you get from these chips has not increased massively. At the same time, using a line card that I'm familiar with, but you can choose your own, and you'll probably get something similar. We've gone from a 40 gig line card in 2008 to something of the order of 260 gig a couple of years ago, and we're expecting to have a half terabit line card this year. And these are edge line cards. The core line cards are much faster, but they're working on different things. As I said, the problem that I want to focus on is on the edge. So you can use your own numbers for CPUs. You can use your own numbers for line cards that you're familiar with. I don't think you'll see something dramatically different. And so, again, like I said, I don't want you to get hung up on the numbers. What I've done is taken the highest end CPUs and to show the growth and to show what can be done in CPUs. Typically, we don't use the highest end CPUs. I don't think anyone uses the most highest end CPUs for the control plane. Also, the pass mark numbers are an average of many, many different things, probably including floating point and graphics and stuff, which we don't typically need in our control planes. These are just an indication of what is the growth of CPU, what is the growth we can expect in control planes, and against the growth that we do see in the data plane. And this is what I'm trying to compare. So the takeaway here is that the year-on-year growth in CPUs doesn't come anywhere near the year-on-year growth in data plane. And we believe this trend will continue for a while. And sometimes, like I said, we keep this trend going by using specialized memory, by using other specialized techniques, which the CPU vendors don't want to do. So there isn't one answer to the problem of what is the right amount of control plane to data plane. Depending on the use case, depending on the app that you have, you might have an average size control plane. You might have a very heavy control plane for the same data plane. Or in some cases, like maybe peering, you have a relatively small control plane. Maybe you want lots of memory, but you don't need a lot of control plane. So there are two problems. One is that the control plane is not keeping up with the data plane, and the second is that you want this flexibility between the control plane and data plane. For a given data plane, if this was your mythical 10 terabit box, depending on the application you have, you might want so much control plane, so much control plane, or so much control plane. The thing is, there is a pressing problem to solve here, and we are instead, following the thundering herd and talking about control plane, data plane separation, and southbound interfaces. And is OpenFlow it? If OpenFlow is not it, do we do an OpenFlow 2.0? We're following that herd, and I'm saying maybe we should change course a bit. So there are several solutions possible. One of them is to put multiple control planes on the same box, on the same data plane. This has been tried before. I'm not saying that this is something new. So essentially, depending on your app, you say, I want one control plane, 2, 4, or more control planes running on the same box, depending on the use case. A different idea is to take ideas from, a different approach is to take ideas from the Web 2.0 companies that really work well with scale out and say, here's my unit. As I add data plane, I'm also going to add control plane to it. And depending on how my bandwidth grows, I'm just going to throw not data plane at it, but a combination of data plane and control plane. And of course, the favorite that everyone says, the answer is in the cloud. So here the idea is that I have this data plane, I have a data control network that will connect my data plane to a pool of resources, and I will implement my control plane in this pool of resources, and I will flexibly allocate more or less resources depending on my use case, depending on what's currently happening. If there's, if I anticipate a big churn in my network, I might spin up more resources. When they're done, I can spin them down. Note that this does not mean changing the southbound interface. So whatever southbound interface I have between my control plane and data plane today, I could use it. I just have to make sure that it can run over a couple of hops, which is this data control network. So it's a different problem to focus on the southbound, and it's a different problem to focus on matching the control plane capability to the data plane requirements. So there are these solutions. There definitely could be others. The important thing that I want to put in front of you is, we need to think about this. We need to understand the numbers and understand where the data plane is growing, where the control plane is growing, and what our need for control plane is going to be doing over the next few years. So far we've ignored this problem, or at least by and large, the industry has ignored it. In pockets, I think there are people thinking about it. This control plane, data plane divide is serious, and you can't just look to the CPU vendors to say, I want you guys to solve it. Just ramp up the cores or ramp up something and just make the problem go away. If they're not going to solve it, we have to say architecturally, this is how we're going to build our boxes. This is how we're going to map our control planes and data planes. This is how we're going to get rid of this impedance mismatch that we see. And the realities that we have to face are bandwidth is growing and is going to continue growing. And I didn't even mention the Internet of Things, which will add huge amounts of bandwidth, maybe in small chunks, but just with a huge number behind it, and add a huge amount of control plane requirements. And we can't just throw this over to the CPU vendors and say, deal with it. We're matching the bandwidth requirements are coming from the network by increasing the bandwidth of our line cards, but we're not anywhere near that with the control plane. So if we acknowledge the problem, is always the first step, then we can start finding ways to address it, find alternatives to the approaches I mentioned, or maybe some new ones. But acknowledge the problem and start working on this. So the conclusion is essentially that the noise of this whole control plane, data plane separation, from the point of view of I can put my control plane anywhere and I can have this open, standards-based or open source or whatever your favorite thing is, control plane, data plane protocol or southbound protocol, that noise has blinded us to a real problem that we have. Changing the control plane, data plane protocol or trying to standardize it has a lot of its own problems, which is how do I optimize for the different control planes and data planes that we already have? If I were to take the protocols we use between our, what we call a routing engine and forwarding engine, and give it to Dave and say, put it on your box, he'd say, whoa, whoa. But if he turned around and said, take mine and put it on your box, I'd have the same hesitation. So changing that protocol should not be our first order of business. Recognizing that the control plane, data plane are not matched, and they will continue, the mismatch will get worse, is what we should be doing, and then say, how do we solve this? And finding, and not just finding a solution to this, but finding one that says, I can size the control plane to the data plane, not just to the data plane, but to the use that you're putting it to. So if you're doing something on the edge, but related to peering, maybe I want one size of control plane. If I'm doing something with mobile or wireline subscribers, maybe I want a different one. So solve the problem and solve it in a way that's flexible. Thank you.
Thank you, Kireeti. Okay, Yakov can wait, then I don't comment. Okay, Yakov. Well, before you get microphone, Kireeti brought up an important observation of a control plane and the data plane. Growth rate is different, right? The data plane really go ahead of control plane. How do we solve that problem? With the traditional routing of the new SDN, with the cloud style. So I would like to talk with you offline on the way we're proposing to set up the determined path, and then you have a lot of burden on the monitoring, tracking the states and so on, right?
Sure.
But maybe that's one way to reduce the control plane requirement there. But I would let Yakov ask question. Where's the microphone? Just talk loud first, so we save time.
Okay, I just want, you hear something? Oh, there it is. Just wanted to reinforce your impedance mismatch. Actually, I think I spoke about the same thing here a couple of years ago. There's a really easy way to show that this has to happen, and that's simply the difference between Moore's law and Butter's law. Now, Moore's law says that, well, approximately every 2 years we double the CPU capacity, but there's another law out there. Butter's came from Bell Labs, and he said that the actual optical transmission speeds double about every 9 months. And there you go, done.
Thank you. Thank you.
Any other questions? Mark? Microphone to Mark? Not on.
Sure.
Actually, it's a follow-up to the comment you just made, which is, the thing is that even though the data plane capacity has to increase, the increase in the control plane doesn't have to grow at the same rate. In fact, that's a factor of what do you need to actually do with this increased data plane? What do you actually need to transmit to the control plane and so on? So I understand the argument you're making, but I really have to disagree that these growth rates are directly linked. It depends on very much on what is that control language that you're using between the control plane and the data plane. I also would like for you to respond to the fact that you mentioned that there wasn't a good alternative yet. Well, you know, OpenFlow is a very good alternative for many of us in that regards. So could you comment on these two statements, please?
By the way, Mark is from ONF.
Sure. If you insist. So let me start with the first one. If they put up the slides, maybe you can see this, but on my slide number 9, I basically say that things change. So the fact that I have 10 megabits per user today might mean tomorrow I have 20 megabits. So if I divide the same 10 terabits by the 10 megabits, but then later I divide by 20 megabits, the scale goes down. Having said that, whether you put the control plane, I'm not saying you put the control plane on the box. Whether you put the control plane on the box or somewhere else, there is a control plane need. And that control plane need is not, people are saying that we can do with less control plane, But if there's a reason for that control plane, probably you're going to have to put that control plane somewhere. Whether you put it on the box or somewhere else, you still have to count that. And how you get that to talk to the box effectively is part of what I would like to solve. So I'm not saying that this will be a constant and this is everything you have to do. What I'm saying is the amount of control plane capacity for a given type of use case is going to grow, but we can't grow just by saying the CPU will grow. To your second point about OpenFlow, I really don't want to say much. The protocol between the control plane and data plane, and I wasn't jokingly referring to Dave, Dave's a good friend of mine. We have our proprietary protocols that we've worked on for a long time to achieve the scale, the robustness, the performance, and so on. Going to OpenFlow will not solve that. OpenFlow is this noise that has distracted the industry for a long time. What we do need to say is that control plane, data plane mismatch has to be solved. If we solve it in a good way, then we can come back and say, is there a different southbound that we can work with? I would rather solve it with the southbound we have because we have problems today. Solve that problem first, come back and say, is there a value, is there a practical problem that OpenFlow solves or a standardized, let's not even call it OpenFlow, a standardized southbound solves? If so, sure, let's work on that. Being what we are, we don't have to work on these sequentially. We can work on them in parallel. But solve the problem of control plane, data plane divide, because that mismatch is just going to grow. And the second thing is solve the problem, if there is one, and if you find a benefit, to standardizing the control plane, data plane interaction.
I think we can leave the rest to the debate session, even though that's about
Thank you,
open source and standard. Thank you, Kireeti.
Thank you.